All right, so for one of the final topics in organic chemistry is something called isomers of organic compounds. And there are two general isomers that we concern ourselves with when it comes to organic compounds. We call them CIS isomers or trans isomers, and trans isomers is really short for translational isomers. And that'll be a key thing to remember when you're trying to distinguish between the two. But when I say isomer, what does that word mean? Because we've heard of polymer, monomer, and now isomer. Well, when we say the word isomer, what we mean is it's the same compound and I'll write the same compound formula more specifically, but different structure. Okay, so but different we would say stereo structure, but we can say chemical structure. And what that really means is the way that the compound is going to look is a little different. But if I were to write the empirical formula down, they would appear to be the same. So if we look at these two compounds, the first one would be labeled as, if we have 1, 2, 3, 4, 5 carbons, that would be pent. It's got a double bond here, so that'll be pent-1-ene. And when we look at the second compound, it's a cyclic hydrocarbon, so that would be cyclo. And then we see once again that it has 1, 2, 3, 4, 5. Now none of them are double bonds, so it'll be a cyclopentane. Now these two are isomers of each other. Why? If I were to write the formula, the chemical formula or the empirical formula for pentene, I would write it as, remember for H's, for alkanes you can go 2N. And that would mean that this has 2 times 5, where the N stands for the number of carbons, and that would give us 10 H's. So the chemical formula for this one over here would be C5H10. Now, in a different color over here, if I were to write all the H's in for the cyclopentane, it would look like this. We're given the available spots. We have 2, 4, 6, 8, and 10 hydrogens. And this one as well would be C5H10. Now these two are isomers of each other because pent-1-ene and cyclopentane have the same chemical formula over here, right? So we're going to write same formula, but different structure. And so what we can say for organic chemistry, and I'll put a little asterisk over here, is that isomers are compounds with the same chemical, and by chemical we mean empirical formula, but different structure. And in organic chemistry, different structure would mean different names, because you name a structure based, or you name a compound based on its structure. So for example, these ones below are the compounds below isomers of each other. What we're going to see is when we draw out hexane, hex-1-ine, and cyclohexene, and we count all the carbons and hydrogens, are they going to have the same empirical formulas? And if they do, then they are isomers of each other. So let's say I draw hexane, and we'll draw it pretty quickly here. So we'll draw it in the condensed structure. So we'll go 1, 2, 3, 4, 5, 6, and then we'll add the appropriate H's. And I meant to write the full condensed structure here, but I guess I'll just write the H's as follows. Okay, now I'm going to write hex-1-ein, so this would be 8. And before I do that, what I'm going to do is I'm going to write the chemical formula. So I got 6 carbons, C6. And then if I count all the hydrogens up, I have 14 hydrogens. Okay, and if you're unsure, just count them again or use the formula. All right, so B. For B, hex-1-ein will look like this. The triple bond here. And when I write this formula, again, I count all the carbons and the hydrogens. This ends up being C6H10. And then finally, the cyclohexenes. We're going to go 1, 2, 3, 4, 5, 6. And then we have to have one double bond here. And then we'll put the H's accordingly, and I'll put the H's in a different color so they're a little bit more apparent. Oops, I erased it here, a mistake. And so, again, writing the formula, I see that it's C6. And then when I count the H's, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this one should also be 10 here. So C6H10. And so when we look at these, we can see that these two have the same chemical formula, but different structure. So what that means is, and I'll write it over here, is that B and C are isomers of each other, but hexane is not an isomer because the formula is not the same, right? And I'll just write not an isomer. So for the general strategy on deciding whether compounds are isomers or not, what you should do is, the first thing you should do is, I'll say write the empirical formula. Right? And once you write the empirical formula, really the second step, and it's going to be kind of obvious, but the second step would just be to see if compound formulas match. And if they match, okay, and I'll write here, if yes, then it's an isomer. Okay, they can be isomers of each other. Now, the last type of isomers that we're really concerned with essentially pertain around the double bond. So I have a pair of what we call stereoisomers, both the CIS and TRANS isomers, and basically they're talking about what happens on each side of the carbon in a double bond. So let's say, for example, I have an ethene over here, and on one side of the compound, I have, let's say, 2 chlorines. And on the other side, I have 2 hydrogens. So this here would carry the formula of C2H2Cl2. Now the trans isomer, the translation isomer, would have the same compound revolving around the double bond, right? It's a stereoisomer. And instead of the chlorines being on completely one side of the carbon or arranged spatially that way, they'll be translated from each other, so almost like a crisscross. So I would have Cl here and H here, and Cl at the bottom and H at the bottom. Now this formula would still be C2H2Cl2, but this spatial arrangement, particularly here, okay, and I would say even more so, specifically the chlorines over here, will lead to a different stability structure. The trans isomers, the ones that vary, you can say translationally or a crisscross, are more stable than cis isomers, and we're going to write due to the partial negative and partial positive that often gets formed. And so by that I mean that if I go back to electronegativities, and I would see that this has a higher electronegativity than hydrogen, I would have chlorine as the partial negative, hydrogen as the partial positive, and you would get somewhat of a dipole moment over here. And that would create a stronger bond, right, or even stronger intermolecular force, versus this one, in which no dipole exists, because it would have the both same electronegativity. So what I would want you to understand from this is that stereoisomers, in particular, just the way the atoms are spatially arranged around the center atom, so the double bonded carbons here, if we have a situation in which we have, let's say, the Cl's, both of them on one side of the molecule, and the H's on the other side of the molecule, all of them in the same place, this would be a cis isomer. And in the other case, where I have a bit of a crisscross, where on one end, at the top, you could say, of the double bonded carbons, I have a hydrogen and a chlorine, or a partial positive and a partial negative. And on the other side, I have a partial negative and a partial positive, so a bit of a crisscross. Then I have a trans isomer.